The first row contains potassium. Potassium has the symbol K, and the 39 indicates its atomic mass. Well, if you look up potassium, you'll find out that its atomic number is 19, so it has 19 protons in the nucleus. And again, any element with 19 protons in the nucleus is potassium. That must mean that it must have 20 neutrons to make a total of 39 nucleons or nuclear particles. And since it's a neutral species, the number of electrons has to equal the number of protons. Both have 19. In the second row, we see an element whose atomic number is 53 protons in the nucleus, and that turns out to be iodine. With 74 neutrons, the total atomic mass is 127. So we could put 53 down here, but again, that would be redundant, since it's iodine, it has to have 53 protons. And the name is IOD. Iron 3 is a cation, or positive ion, with a +3 charge. If it's iron, it must have 26 protons. All iron atoms have 26 protons, and that must mean this isotope has 30 neutrons. For it to have a +3 charge, one of two things would have to be true. You'd either have to increase its atomic number by 3, but then it wouldn't be iron anymore, or you'd have to remove 3 of its electrons. So instead of 26 electrons, which it would have in the neutral iron atom, the iron 3 species has 23 electrons, and we call this iron 3. Okay, so then we get to the issue of average atomic weight. Note here that carbon-12, the isotope of carbon with 6 protons and 6 neutrons, has an atomic mass of exactly 12 atomic mass units. An atomic mass unit is a unit of mass, just like gram. And the conversion between the two is here. You can see it's a very small number because protons and neutrons have very, very small masses. So an atomic mass unit is about the weight of a proton or a neutron. In fact, its definition is that 12 atomic mass units is the exact mass of the carbon-12 nucleus. But if you look at the periodic table, you'll see that carbon's atomic mass is not listed as 12.00, but rather 12.01. And the question is why? If by definition the mass of carbon-12 is 12.00, the only way that mass could be 12.01 is if another species were there, adding to the average mass. And indeed, it turns out that while 98.93% of carbon atoms found in any sample are carbon-12, 1.03% are carbon-13, and the rest are other elements. So, that means the average atomic mass will be, and this is what's known as a weighted average, it'll be the sum, and we do that with the sigma, of the masses of each isotope times the abundance. The abundances should be given as fractions, so 98.93% is 0.9893. So we can calculate the average as the mass, which is 12.00 AMU for isotope 12, times its abundance, which is 0.9893, plus the mass of the other isotope, which is 13.00335 AMU, times its abundance, which is going to be 0.0103. And if you do that arithmetic, it turns out that you get 12.01 AMU as the average atomic mass of carbon. The other 0.04%, this doesn't quite add up to 100%, the other 0.04% is carbon-14, which is radioactive. And in fact, one of the ways we do radioactive dating is with carbon-14. Okay, well, here's a problem that takes a slightly different slant. Notice that the average atomic weight of copper is 63.564. And we can explain that because copper consists of two dominant isotopes, copper-63, with an atomic mass of 63 AMU, and copper 65 with an atomic mass of 65. Again, the numbers are slightly different than that, but for purposes of this problem, let's call copper 63's mass 63 and copper 65's mass 65. Based on the atomic weight, the question would be, what are the percentages of copper 63 and copper 65 in the sample? We notice we have answers that range all the way from 90-10 to 25-75. Now, to do a problem like this, we need to take two pieces of information and combine them to solve the problem. But before we do that, let's look at the problem from the standpoint of what's likely to be the answer. Notice that if equal amounts of copper 63 and copper 65 were present in a sample of copper, you would expect the average atomic weight to be right in the middle, or at exactly 64. But it isn't. It's much closer to copper 63. It's 63.5. That has to mean that there's more copper 63 in the sample than there is copper 65. So the percentages which show more 65 can't be right. And what's more, we know that if it were 50-50, the average mass would be 64. So that can't be right either. So it's got to be one of these two choices that's the right answer. So how would we go about finding out the right answer? Well, we realize that the average, which is 63.564, is equal to the mass of the first isotope, which we'll call 63.0 AMU, times its abundance. Well, that's the question, so we'll call its abundance X. And then the mass of the other isotope, which is 65.0 AMU, times its abundance. Well, we don't know its abundance either, but we can't use another variable because we only have one equation. On the other hand, we know there's a relationship between the abundance of 63 and the abundance of 65, since they're the only two isotopes in the sample. If, for example, 75% of the sample is 63, the other 25 has to be 65. In other words, each of these percentages have to add up to 100%, and therefore each of the fractions have to add up to 1. So the fraction of the sample that is isotope 63 is given by X. That would mean the fraction of the sample that's isotope 65 is going to be 1 minus X. And this problem we can solve. The way we go about that is that we multiply out our terms. 63.564 is going to be 63.0 AMU times X plus 65.0 AMU minus 65.0 AMU times X. Now, if we combine terms, 65.0 AMU minus 63.0 AMU times X equals 65.0 minus 63.564. If you do the arithmetic, that will give you X equal to 0.718, or about 75%.